Many autonomous systems must reason about uncertainty when planning a path through their environment. For example, an autonomous underwater vehicle must deal with unexpected ocean currents when navigating obstacles on the sea floor. Unfortunately, path planning under uncertainty is often intractable in even the simplest scenarios. This is because one must compute complex integrals to evaluate chance constraints and the expected path cost. The situation is made more difficult by complicated geometries. Many methods have been developed that make planning under uncertainty tractable by approximating the underlying stochastic process. An approximation is generated a priori and then used in search algorithms to output a control policy. Clearly, there's a trade-off between the stochastic model's precision and the speed with which a policy can be derived. Our chief contribution is an approach where the precision with which we evaluate the stochastic model can be dynamically varied such that the search algorithm spends more time evaluating paths that are best. For example, when searching for a path, we start by evaluating paths through the environment very rapidly using low precision. When we are further along in the algorithm, we prune paths by increasing our model's precision. Thus, we spend more time reasoning about paths that are closer to optimal. To do this, we develop a bounding numerical approximation to the expected cost function. We discretize the support of the state distribution at each step so that we can increase the precision with which we evaluate the stochastic path cost as necessary. This is shown in the two figures on the right. These graphs show example state distributions at two discrete time steps centered around mu1 and mu2. Level 1 might be what happens in an early stage of the algorithm. At level 1, the numerical approximation of the expected cost uses only 4 regions. What's important about developing a bound on the expected cost is that we can use in a search routine to prune areas of the state space that cannot be optimal. As shown on this plot, as we increase the number of discretizations, the bound on our expected cost become tighter, but take longer to compute. Our algorithm proceeds by using a hybrid search. We use a branch and bound graph search as a region planner and a convex optimization routine as a path planner through a set of regions. A convex form of the problem's chance constraint that allows us to use a fast convex optimization routine for evaluating the cost of paths is used. Next, the region planner is a branch and bound search that chooses which of the convex subregions to send to the convex optimization routine. The branch and bound search effectively prunes paths that cannot be optimal using our bounding method. Test cases were performed on the Slocum glider AUV and a quadrotor navigating city streets. The method outperformed existing approaches in terms of speed and risk conservativeness.